Here we're given a homogeneous differential equation with initial conditions. And we're first asked to apply the Laplace transform and solve for big Y of s, which equals the Laplace transform of y, and then we'll solve the initial value problem by using the inverse Laplace transform to determine y of t, which is the particular solution, where y of t equals the inverse Laplace transform of big Y of s. So the first step is to take the Laplace transform of both sides of the differential equation. So we'd have the Laplace transform of y double prime plus 6y prime plus 8y equals the Laplace transform of 0. And now we'll use linearity, or the properties of Laplace transforms, and rewrite the left side. Let's write the left side as the Laplace transform of y double prime plus 6 times the Laplace transform of y prime plus 8 times the Laplace transform of y equals the Laplace transform of 0. Now determine each Laplace transform. The Laplace transform of y double prime is s squared times big Y of s minus s times y of 0 minus y prime of 0. Then we have plus 6 times the Laplace transform of y prime, which equals s times big Y of s minus y of 0. And then we have plus 8 times the Laplace transform of y, which is big Y of s. We have 8 times big Y of s, and the Laplace transform of 0 is 0. And now let's close the parentheses here by distributing 6. Everything else will remain the same. So distributing, we have plus 6s times big Y of s minus 6 times y of 0. And now using the initial conditions, we'll substitute negative 2 for y of 0 and 0 for y prime of 0. So we'll substitute negative 2 here, and substitute 0 here. So we'd have s squared times big Y of s. Here we're going to have minus s times y of 0, which is minus s times negative 2, so we have plus 2s. Y prime of 0 is 0, so this term drops out, and we have plus 6s times big Y of s. Here we have minus 6 times y of 0, which is minus 6 times negative 2, so we have plus 12, plus 8 times big Y of s equals 0. For our next step, notice how these three terms contain a factor of big Y of s. So we'll factor out big Y of s from these three terms, then we'll also subtract 2s on both sides, and subtract 12 on both sides to move these two terms to the right side. So we'd have big Y of s times the quantity s squared plus 6s plus 8 equals negative 2s minus 12. Let's continue on the next slide. So for our last step to find big Y of s, which is the Laplace transform of y, we'll divide both sides of the equation by the quantity s squared plus 6s plus 8. So simplifying, we have big Y of s equals the quantity negative 2s minus 12 divided by the quantity s squared plus 6s plus 8. Notice how if we wanted to, we could also factor the numerator and denominator. We could factor the numerator and write this as negative 2 times the quantity s plus 6, and the denominator is a product of two binomials, where we'd have s and s. The factors of 8 that add to 6 are positive 2 and positive 4. Let's go ahead and just enter big Y of s in the non-factored form, or this form here. So going back to the first slide, big Y of s is equal to the quantity negative 2s minus 12 divided by the quantity s squared plus 6s plus 8. And now we want to solve the initial value problem by determining the inverse Laplace transform of big Y of s. Before we do this though, we do want to write big Y of s as a sum of two fractions, by performing partial fraction decomposition on this fraction here. So let's go ahead and do that now. So we have negative 2 times the quantity s plus 6 divided by the quantity s plus 2 times the quantity s plus 4. Notice our denominator contains two linear factors, so we'll have a divided by the quantity s plus 2 plus b divided by the quantity s plus 4. So to find the basic equation, we'll multiply both sides of this equation by the least common denominator, which is the quantity s plus 2 times the quantity s plus 4. So we multiply both sides of the equation by those two factors. We'd have the basic equation negative 2 times the quantity s plus 6 equals, when multiplying this first fraction by the two binomial factors, s plus 2 would simplify out. We'd be left with a times the quantity s plus 4, and then when multiplying by this fraction, the factor of s plus 4 would simplify out, leaving us with plus b times the quantity s plus 2. And now to find the values of a and b, we'll select convenient values of s. So let's set s equal negative 4. That would make this first factor equal to 0. So when s is negative 4, here we'd have negative 2 times the quantity negative 4 plus 6, that's positive 2. So we'd have negative 4 equals, this factor would be 0, and here we'd have b times the quantity negative 4 plus 2, so we'd have negative 2b. So notice how this tells us that b is equal to positive 2. And now let's select s equals negative 2, which will make this factor 0. So if s is negative 2, here we'd have negative 2 times positive 4, which is negative 8, equals, this would be a times positive 2, or 2a, and this would be 0, so we'd have a equals negative 4. Which means you can write big Y of s as a over s plus 2, which should be negative 4 over the quantity s plus 2, and b is positive 2, so we'd have plus 2 divided by the quantity s plus 4. And now we'll take this form of big Y of s and take the inverse Laplace transform of both sides of the equation. So we'd have the inverse Laplace transform of big Y of s equals the inverse Laplace transform of, instead of having this negative term first, let's write this as 2 over the quantity s plus 4 minus 4 over the quantity s plus 2. Now on the left side, the inverse Laplace transform of big Y of s is y of t. So we have y of t equals, let's rewrite the right side as 2 times the inverse Laplace transform of, the numerator would now be 1 divided by, now looking at the table of Laplace transforms, notice how we need the denominator to be in the form of s minus a. Let's write s plus 4 as s minus negative 4. And then we'd have minus 4 times the inverse Laplace transform of 1 divided by the quantity. Again, let's write s plus 2 as s minus negative 2. So we have y of t equals 2 times, notice how this now fits the form perfectly of 1 over the quantity s minus a, where a is negative 4, so the inverse Laplace transform is e raised to the power of negative 4t. So we have 2 times e raised to the power of negative 4t, and then we have minus 4 times, and again notice how this fits the form perfectly where a equals negative 2, so the inverse Laplace transform is e raised to the power of negative 2t. So here we have minus 4 times e raised to the power of negative 2t, which means the particular solution is y of t equals 2 times e raised to the power of negative 4t minus 4 times e raised to the power of negative 2t. So going back to the first slide, using the Laplace transform to solve this initial value problem was not the fastest way. It would have been much easier just to use a characteristic equation. But either way, we did find the particular solution is y of t equals 2 times e raised to the power of negative 4t minus 4 times e raised to the power of negative 2t. I hope you found this helpful.